Group 17 elements. Group 17 have fluorine, chlorine, bromine, iodine and astatine. All these elements in group 17 known as halogen. The outermost electronic configuration in halogens is Ns2 Np5. These elements exist in nature in form of fluorides like fluorspar, calcium fluoride, cryolite, which is sodium hexafluoroaluminum, and fluorapatite, which is nothing but calcium phosphate, calcium fluoride. These halogens exist in seawater in form of soluble salts of sodium like sodium chloride, but also bromides and iodides of sodium, potassium, magnesium and calcium are present in seawater. Now, physical properties of halogens. All halogens are colored due to absorption of visible part of radiation. This visible radiation excites outer electrons to a higher energy level. The color displayed by halogens is complementary to the energy of radiation absorbed for excitation. The light emitted by the halogens is of increasing energy level in visible spectrum. As we go down the group, which means light absorbed is of lower down the group. Let's see, this is a video. We observe the color of fluorine as yellow, which is here. So it means its complementary color will be on the higher side. Higher energy near violet radiation will be absorbed by fluorine for excitation. Chlorine near greenish, it will be of a bit lower energy. Bromine is going toward reddish, so energy will be of lower side. Iodine, which is going to velvet, energy is to tilt toward red end. Among the other physical properties of halogens, we have melting points, boiling points, density, interatomic distance between halogen atoms. These are basically covalent molecules, bond association energies, and standard electrode potential. Here we see a trend. The melting and boiling points keep on increasing because of enhanced van der Waals forces that increases with increase in atomic size. Density, it again increases down the group. Interatomic bond length, obviously it will increase down the group. Bond association energy will reduce. But here we see there is a kink. First it increases, then start decreasing. We'll try to explain it. And standard electrode potentials, it keep on decreasing down the group. Bond association energy of fluorine is less than chlorine and bromine, because the reason is simple. For fluorine, we having a inter-electronic repulsions. The repulsions between lone pairs of electrons present upon small-sized fluorine atoms and the smaller bond distance. That is the reason In this group, bond association energy is highest for chlorine. So electronic and electronic repulsions are responsible. You see here, these electronic clouds in fluorine will repel each other. That causes the lower bond association energy. Further, halogen group have a little tendency to lose electrons because they require just one electron to acquire stable electronic configuration. And in such a case, due to increased in atomic size, ionization enthalpy decreases down the group. As you move down, ionization enthalpy will reduce because of increased atomic size. But ionization enthalpy for individual elements in their period will be among the highest after noble gases. As small size of fluorine atom, there are strong inter-electronic repulsions we already know. So, the electron gain enthalpy will have certain problems because addition of another electron to a high electron density fluorine atoms is not easy. For the same reason, the electron gain enthalpy for fluorine is less than chlorine. Having a fluorine atom, and these are the electronic configuration. One unpaired 2p electron, but because of the presence of all other electrons, addition of a new electron is not that easy. That offers a huge repulsion to the incoming electron. All these electrons because of the small size of fluorine atom. But that problem is not there in chlorine. In chlorine, what happens? The space is larger and it has to go to 3p orbital, which is spatially large in size compared to 2p. That is the reason electron gain enthalpy of chlorine is better than fluorine. Coming to the chemical properties. Halogens exhibit -1 oxidation state. However, chlorine, bromine and iodine exhibit plus oxidation state up to from +1 to +7 as well. This is possible only when it binds to most electroactive element, that is fluorine. In ground state, first excited state, we are having a unpairing of one electron that moves to d orbital. Second excited state, another electrons from np orbital moves to d orbital. Third excited state, all unpaired electrons we have it. Depending upon the number of anions or atoms or molecules bound to the halogen atom, we will have different oxidation state. In case only one group binds to halogen, +1. In case of having 3 groups binding, +3, 5 groups binding, +5, 7 groups binding, +7 oxidation state. Reaction with water. Fluorine oxidizes water to oxygen because of its very high standard electrode potential. It having a strong tendency to get reduced, so it oxidizes oxygen from water. That's what happens when we bubble a fluorine gas through water. We are getting hydrogen liberation and HF and When we pass a chlorine gas, what happens? We're getting a HCl as well as HOCl, which is hypochlorous acid. For bromine, we pass a bromine through water. Again, we were getting a hypohalous acid plus HBr. That's what we are going to get. But in case of iodine, the reaction of iodine with water is non-spontaneous. Reason is, as iodine oxidizes water to form iodide. Iodide can be oxidized by the oxygen in acidic medium back to iodine. First, we get a iodic acid and oxygen liberation. In the very next step, this liberated oxygen, will oxidize this iodide back into iodine. That is the reason it is a non-spontaneous reaction. Oxoacids of halogens. Halogen form several oxoacids, and most of them are stable only in aqueous solutions or in form of their salts, hence we can't isolate them in their pure form. Probably interhalogen compounds are very important to study when we're talking about halogen group. Two different halogen reacts with each other to make interhalogen compounds. General composition can be single halogen, XX3, XX5 or XX7. This is possible. Here this X is larger size halogen and X slash is small size halogen that binds to it. Basically this is cationic, this is anionic. And that is the reason it is cationic, because it's less electronegative than X dash. As the ratio between the radii of X and X dash increases, the number of atoms around the central atom, that is the covalency, also increases. Like we can expect the ratio of the radii iodide to fluoride can be highest, or iodine to fluorine can be highest, so their covalency will be highest. This is XX-1. We are having a ClF, BrF, IBr. These are the three possible compounds, interhalogen compounds. Chlorine, which is smaller, which is larger in size compared to fluoride. Chlorofluoride, bromofluoride. Here iodobromide. This is a black solid. Pale brown gas. This is a colorless gas. Next possibility we know, XX-3 means ClF3 BrF3 IF3 ICl3. First is colorless gas. This is a yellow-green liquid, yellow powder, orange solid. ICl3 is orange solid. All these having a bent T sort of structure, presence of two lone pair of electrons. Now third is XX5 hash, IF5, BrF5, ClF5 are possibilities, and all these have a square pyramidal geometry. First IF5 will be colorless gas. Remember, most of the fluorides we have saw here are gases with chlorine and fluorine. Iodo F6 is a colorless gas. Bromo pentafluoride is a colorless liquid. Chloropentafluoride is colorless liquid again. Last in the category is XX7 hash. This dash compound will be IF7 only possibility. It's a colorless gas. Pentagonal bipyramidal is its geometry. These are all covalent molecules and are diamagnetic in nature. Except fluorine, interhalogen compounds are more reactive than the halogens. I mean, they more than except fluorine, which is more reactive than all these compounds. These interhalogen compounds are always more reactive than any of their parent individual halogens. Like XX dash bond will be always be weaker than any XX bond in halogens. So it will be more reactive. Bromo trifluoride will be more reactive than individual bromine or fluorine. These compounds undergo hydrolysis, giving halites as well as the acids, and we are getting a hypohalite, halite, halate, perhalate. When we will get these compounds, like these we get smaller halogen and the hypohalite. In case of X dash hypohalite X-3, tri halite compounds, interhalogen compounds, we get halite, halate for pentavalent compounds, and perhalate for using heptavalent compounds. H2X get. Now first reaction, iodobromide, we react with it, we are getting, according to hypoiodus acid we get with HBr, IBr3 reacts with water to give us iodous acid with bromide, 3 HBr molecules, IBr5 reacts with HIO3, remember this will react, 5 HF molecules will go out. Anionic species will goes out as acid, halo acid, and cationic species will make, here we getting a chlorate, iodate, here iodic acid. IF7 will give us periodic acid and hydrogen fluoride. So remember again, monovalent compound will give us hypohalite. Here we are getting hypoiodus acid. Trivalent will give us halite, which is nothing but iodous. Pentavalent will give us halate, which is nothing but iodic. And heptavalent will give us periodic acid.